All right, now let's begin. Basic chemistry. All right, so these are the basic units of chemistry. 1 mole. I feel like online you should have seen a good chunk of jokes about this unit. Now, a mole, it's a representation of a pile of particles or atoms or molecules. This difference you should remember from taking Regents chemistry. Uh, Now, a mole of a certain substance, this can be weighed, its mass can be weighed through grams usually, and two terms that you're going to see pretty commonly are gram formula mass and gram molecular mass. What these units represent is the weight, is not the weight, is the mass in grams of a mole of a certain substance. And you can use this through dimensional analysis, aka proportions, just like how you use in linear algebra, to make conversions from 1 mole of a certain substance to its mass. Now, a mole of a gas can be measured through liters, and this is a unit of measurement of volume. And at STP, which is standard temperature and pressure, I'll go over what that means later, in case there's somebody forgot from Regents chemistry. 1 mole of any gas occupies 22.4 liters of volume at standard temperature and pressure. Now, 1 mole of a certain substance also has a certain number of molecules. All right, let's continue. Where was I? All right, yeah, so 1 mole of a certain substance has a certain number of molecules. This is called Avogadro's number. I hope you remember that from Regents chemistry. This is the number of molecules in 1 mole of a substance, or 22.4 liters of a certain gas, or the certain mass, I guess. Yeah, the gram formula mass of a certain substance. There are 6.02 times 10 to the 23rd molecules inside 1 mole of a certain substance. Now, this number will not change under conditions of different temperature or different pressure. The one that you need to worry about for temperature and pressure is volume. Now, some units to express concentration. The first one, the most common one that you should see through stoichiometry and equilibrium for the Science Olympiad event is molarity. Now, molarity is used to represent the concentration of a certain solution. Now, the parts of the solution, there is a solvent, there is a solute, and there is the whole thing, which is the solution. The solute is the thing that you're adding to a certain liquid. So let's say I was making, I'm going to use this analogy again, I guess. Let's say I was making soup, a really bland soup that was just water, and I added salt to it, and that's my soup. The salt that I would add to the liquid, to the water, that salt would be the solute that I'm adding to a solution. And the liquid aspect, that is what we would call the solvent. So the solute is the salt, the solvent is the liquid, and the solution is the resultant of adding that salt to the water. That is the solution. The solution is both the solute and the solvent. Now, molarity represents the moles of a solute. As I mentioned before, a mole is a pile of molecules, particles, or atoms, and this is for every 1 liter of a certain solution. So if I had 2 moles of salt and I added it to 2 liters of water, let's say the volume of the salt was negligible, that means the concentration would be 1 molar, because that's the units in molarity. Now, molality is slightly different, but also pretty similar. It takes the moles of the solute, that's the amount of piles of the salt that we're adding to our said soup. This is per 1 kilogram of solvent, which is the water. Now, rather than taking the mass of the whole solution, which includes the mass of the solute, this just only worries about the liquid. So that's the difference between molality and molarity. Percent by mass and percent by volume are pretty similar. You take the mass of the solute, the thing that you're adding to the solution, and you divide this by the total mass of the whole solution, including that solute, and then you multiply that by 100. This is the same case for volume, percent by volume, but now instead of taking the mass, you're taking the volume of both the solute and the solution. Now, in this case, for percent by mass and percent by volume, it doesn't matter whether or not you use kilograms, grams, liters, milliliters. All that matters is that the units are the same for both the solute side and the solution side. Now with molarity and molality, you do have to specifically use moles and volume and moles and kilogram. You have to use liters and kilogram. You can't use milliliters, you can't use grams, you can't use decigrams. You have to stick with those units. Now, this fifth unit is parts per million. This is for solutions that have a really small concentration of something. You might see this in the water quality reports that our school gives us. Those water quality reports, they probably say parts per million because the amount of solute that is present in our school water is probably a really, really small percentage. So it's easier to understand when you say parts per million instead of percent by mass or percent by volume. So parts per million, the way you calculate this is you take the mass of the solute, you divide it by the mass of the solution, and you multiply that by 10 to the 6, aka 1 million. And so this way you get a more clear picture of the concentration of a certain solute in a solution. Does anybody have any questions about this before I go on? Now, standard temperature and pressure. Now, this is what I mentioned before about the 1 mole of any gas occupying 22.4 liters of volume. Now, this is a set of conditions that scientists use in their experiments sometimes, but mainly you'll only see in calculations, not really in real life experiments too often. Now, the standard temperature that is being referred to is 273 Kelvin, 0 degrees Celsius, and 32 degrees Fahrenheit. Now, all of these 273 Kelvin, 0 degrees Celsius, 32 degrees Fahrenheit, they all equate to the same temperature. Now, how you convert to it is pretty easy, but for Kelvin and degrees Celsius, you take the degrees Celsius and you add 273, and from there you get the Kelvin. I think that might have been a part of your initial assessment that you just took earlier. So if you're wondering how, that's how, in case you forgot that from when you learned it at some other point. Now, degrees Celsius can be converted to Fahrenheit by subtracting 32 from the degrees Fahrenheit and multiplying that by 5/9. Now, you won't really see the second one too much, but you will see the conversion between Kelvin and Celsius really often. So it's good that the conversion between those is pretty easy. Just add 273. Now for pressure. The standard pressure that is being referred to is 760 millimeters of mercury, which is Hg. The symbol for mercury is Hg on the periodic table. This is also equal to 760 torr. This is equal to 101.3 kilopascals, and this is also equal to 1 atm or 1 atmosphere. Now the conversion between millimeters mercury and torr is simply 1-to-1, and from there you can use proportions to figure out any other conversion you need to based on these 4 pressure conditions. Does anybody have any questions? All right, I'm going to move on. Unmute if you do you have any questions because I can't see the Discord call right now. All right, now it's time to move on to gas stoichiometry. Now this is, I'm going to talk about the kinetic molecular theory of gases now. In order to understand the mathematical side of chemical reactions, you first need to understand how gases actually interact with each other, because that's the basis for our calculations. Now this slide talks about the aspects of an ideal gas. So ideal gases, they consist of tiny small particles that are separated so far apart and have so many empty spaces that it's considered they don't occupy any volume and they don't have any mass because they are so small and because they are so far apart. Now, gas particles within the gas, they move in a random straight line motion, not curved, and the collisions between these gas particles are elastic. And collision can be considered elastic when these certain particles, they collide and then they separate with no change in momentum or kinetic energy. And you can see that all around us. If you make an observation just about the room that you're sitting in right now, the temperature doesn't wildly change all of a sudden, despite the fact that there's so much gas around you, and there's high probability that they're for sure colliding with each other, but the temperature of the room does not change, so that means that there's no change in kinetic energy and no change in momentum. Now, at a given temperature, the kinetic energy remains constant. That's what you said just before. And number 8 and 9, they do cover stuff that's going to be elaborated on later in different slides. Now, for rule number 8, lighter gases, they will diffuse faster than heavier gases. That feels pretty intuitive if you really think about it. And number 9, there are no forces of attraction or repulsion between gas particles. Now this is all under ideal circumstances. Two different gas particles, they won't really attract each other, they won't repel each other. That's it. But now we don't exactly live in an ideal world. We live in the real world. So real gases, they behave differently from ideal gases. Real gases have a volume that is not negligible. This is something that we do actually have to account for. And gas particles, they do actually have weak forces of attraction to one another. I'm sure if you remember from Regis chemistry, I forgot which were these. I think these van der Waals. For those of you who took AP Chem, that would be London forces of attraction, or LDF. And in order to make real gases behave like ideal gases in certain experiments, because sometimes that's more helpful, you'd want to increase the temperature and decrease the pressure. Why, you may ask? Well, increasing the temperature and decreasing the pressure will increase the amount of volume that a certain gas will have, and when you increase that volume, it will make it behave more like an ideal gas, because as you said earlier, ideal gases, they have no volume. Their particles are spread so far apart that it might as well be considered that they don't have a volume. So increasing the temperature and decreasing the pressure in these experimental conditions, they can make the gases that you're experimenting on behave more ideally. Does anybody have any questions about the kinetic molecular theory of gases? All right, if no one has any questions, I'm going to move on. Now, air pressure. Air pressure can be measured through a mercury barometer. If you remember the units I said earlier, I said millimeters of mercury. This is why. The image that you see on the right is a picture of a mercury barometer. And what this does is it can measure the atmospheric pressure, and the unit that we use is millimeters mercury, because as you see in the apparatus to the right and the barometer, there's an open pool at the bottom, and there's no glass cover on the top. The atmosphere is acting directly on that mercury, and that atmospheric pressure, the pressure that the gases in the atmosphere are generating, they're going to push down on the mercury, and when they do, that mercury is going to travel up that tall tube over there, that tall tube in the middle, and there's a vacuum at the top, so that ensures that the atmosphere is not acting on that mercury tube that's also traveling in that tall tube. That tall tube is closed, so the atmosphere cannot act on that specific surface area. What happens is that will push the mercury up, and the distance that mercury is pushed up, that can be measured and used as a unit of pressure. So at the standard pressure, which is equal to 760 torr, 101.3 kilopascals, 1 atm, this is what is referred to whenever we say standard pressure. And the reason this works is because as the atmosphere has a greater pressure, it will act more on that mercury and will drive that mercury further up that tube. And so when there's greater atmospheric pressure, the mercury will travel further up the tube. This is a direct relationship. If there's lower pressure, the mercury will travel less, and we can record the distance that this travels, and we can use that as a measurement for the pressure of the atmosphere or a certain gas. Now, this is a picture of a manometer. This is similar to a barometer, but rather in here, this is measuring the pressure of a certain gas that you put in this apparatus. Now, what happens is that you have a certain gas in that left aspect of the apparatus, and then from there, you have mercury in the middle. If you leave the right side of it open, and you know the pressure of the atmosphere, you can calculate the pressure of the gas that you have isolated, because as long as if that right end is open-ended, the atmosphere can act on the mercury, pushing it down on that right-hand side of the tube and pushing it up to the left side. So let's look at situation 1, actually. In this situation, the atmosphere is actually acting less on the mercury than the pressure of the gas. That means that the pressure of the gas is larger than the pressure of the atmosphere. And we can measure this difference by just looking at the difference in height of mercury. You can see on model 1, this difference in height is modeled with the arrow, and it says h centimeters. This value in centimeters, this can be used to mathematically calculate the pressure of the gas, as long as if you know the pressure of the atmosphere that is acting on that mercury. We can take that difference, we can add that to our known pressure of the atmosphere, and From there, we can calculate the pressure of the gas that we have isolated inside. In situation 2, where the two levels of mercury are the exact same, this means that the pressure of the atmosphere and the pressure of the gas are acting on the mercury with an equal amount of pressure, which is why they're both at the same level, which means that the pressure of the gas inside is equal to the pressure of the atmosphere. In model 3, we can see that the pressure of the atmosphere is acting more so on that mercury than the pressure of gas, because the pressure of the atmosphere is pushing down on that right hand side and making it raise up on the left side, where the pressure of the gas is acting on this mercury, on this liquid mercury. And so we can calculate the pressure of the gas by taking the pressure of the atmosphere and subtracting it from that difference in height, which is also labeled with an arrow and H. And this difference in height, this represents how much weaker the pressure of the gas is compared to the pressure of the atmosphere. Now, vapor pressure, I'm going to introduce this right now on this slide. When the temperature of a certain liquid will increase, the kinetic energy of that vapor will also increase. And then from there, that will lead to evaporation and what we now coin as vapor pressure. Vapor pressure is essentially the gas molecules that come off of liquids and induce pressure on the environment. Now, when you're boiling a pot of water, as soon as it starts actually boiling, that means that the vapor pressure that the water produces is equal to the atmospheric pressure that is acting on that liquid, that's keeping it a liquid and preventing it from evaporating. But when you heat it up, this will increase the vapor pressure until it eventually equals that of the atmosphere, and then your pot of water can start boiling. Now, if you were to ever go hiking or climbing, and you were on a mountain, you're ever able to reach up to a really high altitude, you notice that when water starts to boil, it's going to be at a lower temperature than it would be if you were at sea level. And what this means is that you're going to have to cook whatever food that you need to for a longer amount of time because that water is boiling earlier than expected. This is because at a higher altitude, the atmospheric pressure is lower. And so because of this, the vapor pressure does not need to be as high in order for it to match that of the atmospheric pressure and for a liquid to start boiling.